Hello everyone, welcome to the first part of a three-part series where we build and simulate a 2 degree of freedom robotic arm in MATLAB Simscape. In this video, we'll start by bringing a CAD model into Simscape. We'll walk through how to set up the mechanical structure, define the joints, and add some basic input signals to see the robot in motion. Whether you are new to Simscape or just looking to strengthen your modeling skills, is the perfect place to start. In the second part of the series, our 2 degree of freedom manipulator, we take things further by introducing trajectory planning, and we'll define a desired path for the robot's end effector and explore how to calculate the forward and inverse kinematics needed for it to follow that path. Can the robot trace the trajectory accurately? We'll find out together. In the final part of our series, we'll switch to torque inputs and design a PID controller for each joint. This brings us closer to how real robot systems are controlled. We'll test whether our robot can still follow a trajectory under more realistic dynamics and analyze how well the controller performs. If you are into control design and robotics, this one's for you. The robot that we are going to simulate today is a planar 2 degree of freedom manipulator, which consists of a base and two links, L1 and L2, and an end effector, which is a cylindrical solid, and two revolute joints, one placed here and one over here. Our reference frame, X and Z in the vertical direction, and Y-axis inside the plane is placed somewhere at the top of the base, which has an offset of D0 with respect to the ground. There are a few parameters that we have defined here for our assembly: D0, L1, and L2. I have created this model in NX. If you have SolidWorks, for example, you could directly export the model into Simscape. If you don't, there's no problem. We just have to export the parts one by one and create step files out of those. And in MATLAB Simscape, we can import those step files to create this assembly. Now we go to MATLAB, and in the command window, we type the name of the model that we are going to create. The command smnew creates a project for us for our model with predefined basic elements in it. So the model that I'm going to create is called Manipulator 2-DOF. It opens up the model with a lot of initially defined blocks that we don't need. We are going to make the model out from scratch. That's why I get rid of these blocks. The only three blocks that I keep are these three, which are important and necessary for each Simscape modeling. So in the configuration, I would see that the gravity vector is defined as 0, 0, minus 9.8, which is correct. The gravity is in minus z direction. That's what we want. There are a few changes that we have to set. In the beginning, I would go to the setting of the solver of the system of the model. I would click here and go to the setting. The default solver is a variable step solver, as it is mentioned over here, that I would like to change to a fixed step. And when I do that, I would also like to change the time step to 0.001. Then I press OK. As I mentioned, there are a few parameters that we need to define our model, D0, L1, and L2, that I would like to define as parameters in my model as well. So I would go to Modeling tab here, and then from this drop-down menu, I select Link to Data Dictionary. In principle, I would like to create a data dictionary in which these parameters are defined and could be referenced in the entire model that I'm going to create. And this window asks us to either create a new file for the parameters or browse into an existing file. So since I don't have that file, I would create it. I would create a new file and asks me to give it a name. I would name it parameters manipulator 2-DOF and save, and then OK. To add those parameters to this dictionary, I would go to, still in the modeling tab, I would go to Model Explorer, and here it's the model we have created so far. We go to the external data, and then we see the file that we just created, parameters manipulator 2-DOF. If I expand it further, there is design tab over here, which is empty, but I would like to create the parameters over here. There are two ways actually to do so. One is to simply define MATLAB variables or define Simulink parameters. That I prefer this one. The reason will be given to you in future videos. Okay, the first parameter that we are going to create is L1, which is 200 millimeters. We don't need to define any dimension here. Then we create another one for L2, which is 145, and a third parameter for D0, which is 55. Okay, close this window. Now we are going to import the base of our assembly. To do so, we could, in the simulation tab, we could go to library browser, which opens up the list of available toolboxes for you in Simulink. And if you scroll down to Simscape, we could go to multi-body, body elements, which shows you basically the different types of elements that you could create: brake solid, cylindrical solid, spherical solid, whatsoever. But what we need is a file solid to be able to import a step file. I simply drag and drop the block over here. Another way is to double click on the main window and type the name of the block if you have it in mind, file solid for example. Okay, I already created it, that's why I double click on the file solid. Now here I import the step file, which is based step file, and if I press the refresh button, you see that it is imported. And in the inertia, I could change the material properties. You could change the density and give it something like 7800 from steel. And if you update, we could see that other mass properties are updated based on the geometry of the part. And in the graphic, we could change the color of the part. I would change it to gray and refresh here, so we see here our part. Here if I press on the frames to see the available frames, we see that the part frame is defined on the ground at the lower surface of the part, but our reference frame, our world frame, is going to be in this region. That's why I would like to perform a rigid transform so that the world frame is connected to the top of the base. So I would first rename it to base. I would also select Ctrl R to rotate the block toward these three blocks. Now I have to perform a rigid transfer in the Z direction downward with the amount of D0 to connect it to the base, because the frame of the base is defined here. So what we should do is to double click. There is a block named rigid transfer. If you make the connection, if I double click it, we mean to move in the Z direction, actually in the minus Z direction for amount of D0. So could go to translation, standard axis, Z direction or minus Z direction, doesn't matter. Could say D0 or minus D0 in the Z direction. Just make sure to change the unit over here to millimeter, and the value is read from the parameters that we defined in the dictionary. So I close this. Now I have the base, which is correctly attached to the world frame. Now here I would like to place my first link, which is link 1. But before that, I would like to have a revolute joint over here. So I have to create a revolute joint between the base and link 1. The way to do so is to double click over here and type revolute joint. Or in another way, we could go here from the joints. You see different types of joints over here, and revolute joint is also over here. If we open revolute joint and go to this description tab, we notice that the rotation that the joint performs is around Z axis. However, in our model, the rotation of joint 1 is around Y axis. So we have to perform a transform to bring the Y axis in the Z direction. In other words, we would like our joints to perform rotation in our reference coordinate in the world frame. That's why we have to change the Z direction of the joint to make it in the Z direction, actually in the Z direction of our model. Therefore, we create another transform . And now we have to perform a rotation around x-axis to bring the y-axis of the joint in the vertical direction, in the Z direction. So standard rotation around standard axis, x 90 degrees. Okay. Now the base of our joint 1 is in our world frame, but we want the output, also the follower, to be in our world frame. That's why we do the reverse of this transform. So I would click and drag to create a copy of this rigid transform and perform connection, and double click on it, and now we perform the reverse, which means minus 90 degrees now with respect to x-axis. Now we could say that the joint 1 is correctly defined in our world frame. Now it is time to create and import the first link. We basically create a copy of this base file. We name it link 1. Double click on it. Import link 1, refresh, and we see the part over here. We don't need to change the inertia if the materials are the same, because it's a copy of the base. We just need to change the visualization and the color. Apply. If we look at the frame that is defined for this part, we see that it is defined right at the left tip of the part. That is exactly where we want it to be, because this is the place where we would like to connect this link 1 to joint 1. So it is okay, and we create this connection. To see how far we are in the modeling, we just press run, and we see that link 1 is freely rotating around joint 1, and it is defined correctly. The reason that it is moving is because of the gravity, and we haven't applied any constraint on it yet. So far so good. In the following, we are going to attach joint 2 and link 2. It is important to note that here that joint 2 is going to be placed here on the other side of the link 1. That is why we have to first perform a rigid transform along the x-axis to create a frame over here on the right side. So I would like to have a rigid transfer again, along the x-axis for L1, 200 millimeter. That is where we are going to create our second joint, which is basically the same joint as joint 1. So I create a copy of joint 1, which is renamed to J2 already, and basically we have to perform the same type of transform before and after the joint to make sure it is properly defined in our world frame. Here we go. And now we could attach our second link. So I create a copy of link 1, which is renamed automatic to link 2. Double click on it, import link 2 step. As you see, it is like this. We just need to change the color to yellow, for example. Apply. Okay. Now if we check the frame, we see it is placed somewhere in the middle of this part of the link, but we don't know for sure if it is in the center or not. That is why we cannot use it properly. We have to define another frame. The way to define a frame, a new frame, is to go over here, frames, new. And in the frame origin, we select based on geometric features. And now I select this surface, this cylindrical surface. If I do so and use selected feature, a new frame is created for me at the center of this cylindrical surface. And that is exactly where I want it to be, because in my model I would like to connect an end effector over here. So I don't need the frame that is defined here, so I uncheck this box and OK. In the model I have now link 2. I rotate the block, but before connecting it to joint 1, joint 1 is defined over here, and the frame that we just defined is placed over here. That is why we have to first perform a rigid transform along the x-axis with amount of L2. So we go to the model and we create another rigid transform. Now it is going to move along x-axis again. The value will be L2. The unit will be millimeter. Okay. Once again, we run the model and you see it is correctly defined. The reason that in appearance it is different from how we show it here, where there are some initial angular values for the joint 1 and 2, is that we haven't defined these initial states for these joints. We could do so actually by going to joint 1, set specified position target, which could be, for example, for link 1 30 degrees, and for joint 2 let's say 45 degrees. And now if we run the model, you see initially it has 2 angular values for each of those joints. We don't have to do it this way. There is a better way to do so. If I undo these changes, just to uncheck these boxes, uncheck, is to perform a rotational rigid transform. To do so, could rigid transform over here. We could place it before joint 1. If I bring it here, and the rotation that we are going to apply to give it an initial condition is around y-axis. Actually, since the y-axis is inside the plane, this angular value is minus 30 degrees, for example. So if we go here, method standard axis around y-axis minus 30, around minus 1 for 30 degrees, doesn't matter. I will not apply it to the other joint, just to give you, I just want to give you a clue how to do that. If I run this model now, as you see, only joint 1 has an initial value of 30 degrees, and joint 2 doesn't have an initial value since I did not apply that transform. But I would like to keep the robot manipulator as it was before, so I get rid of this block and keep it that way. I just wanted to show you how to do that in different ways. Okay, now it's time to connect the last link, which is end effector, to link 2. The way to do so is to create a copy of link 2. Let's call it end effector. Double click on it. Read it from here. Let's change the color to green, for example, and apply. And refresh to see the part. And you see the frame that is defined at the center is exactly what we need actually, because it is connected to link 2 on the same place. And the connection between link 2 and end effector for this example is just a welded connection. So what we do is to create a weld joint. Now if I run the model, you will see how far we are in the modeling. Okay, now it's just time to organize the connection a bit. I would select all these parts to be one single subsystem named link to or L2. All these 3 blocks to be defined as base, and then we have joint 1. All these 4 blocks to be the next subsystem, which is L1, link 1, and then we have J2, link 2, weld joint, and then end effector. At this moment, I would like to create some input signals for the 2 joints to move them and see the robot in action, in motion actually. The way to do so is to go to the joints, and if you go to actuation, we could either actuate the joint by torque or motion. Here I'm going to create a motion profile for each of the joints and move the robot. So in the motion, here I would select provide by input, and the torque is going to be calculated automatically. And I would like to measure the output of the joint and later on check whether it is the same as the input joint angle. So in the sensing, I could select position. I could select also other options like velocity, acceleration, etc. But for now, we don't need that. Just position is sufficient. And you see there are 2 ports created for this joint. One is an input port for the joint angle, and the other one is an output port for the measured joint angle. We basically do the same for second joint, automatically computed torque, and motion provided by input, and position we are going to measure. So we are going to create a ramp signal to rotate the joint 1 at a constant velocity. To do so, I would create a ramp function, and the slope is basically the angular velocity that I'm going to apply to the joint. So if I wanted to rotate at a speed of 10 degrees per second, I would say 2 times pi, which is a full rotation, 360 degrees over 36 gives me 10 degrees per second. And if I try to connect it to the joint, it does not connect. And the reason is this ramp signal is a Simulink signal, while this system is a physical system, and we have to convert this signal into a physical signal. The way to do so is to double click and type for Simulink PS physical system converter. And we basically have to do so before connecting the input ramp to the joint angles. And now you see it is connected. There is little setting we have to change. In the converter, we have to go to input handling, to filter input to create smooth derivatives, and we change the input filtering order to second order filtering. We basically do the same thing for the other joint, only this connection is not created correctly. Okay. And on the other side, we could also measure the joint angles. For that, it is a physical signal, and if you want to show it in a scope or something, we have to first convert it to a Simulink signal. Basically the reverse action of this block. Now we search for physical signal to Simulink converter. So we could create a connection over here, and basically a copy of this we can create for the second joint. Okay, I just forgot that the ramp function that I created for this joint was had a angular velocity of 10 degrees per second, but this also could be the same. We could make it a bit faster, like 20 degrees per second or something whatsoever. And now we are going to compare whether our input signal is equal to the output signal. To do so, we create a scope block, and it has one input, so we would like to show two signals. That's why we need a mux block to embed multiple signals into one. So one of the inputs to this mux block will be our input signal, and the other one will be our measured signal for joint 1. Then now we create this connection. We basically do the same for the other joints. Okay, now we run the model to see how it performs. You see that the two joints are rotating at the defined ramp, actually at the defined angular velocities. And if we go to the first scope, which compares the input and output of the first joint, we see one signal. If we go to view to legend, we realize that there are two signals shown here which are perfectly overlapping each other, which means that the input and output of the joint are precisely the same. I click on the signal, I will see the input. And the same goes for the second joint. That's it for this video. In the next video, we'll define a trajectory for the end effector and check whether our manipulator can follow it using forward and inverse kinematics.